Welcome everybody to this afternoon's talk. My name is Dr. Alan Duffy. I'm a research fellow and astronomer at Swinburne University. I'd like to start today by paying my respects and acknowledging the traditional owners of the land upon which we meet, the Gadigal people of the Aurora Nation, and pay my respects to their elders, past, present, and yet to come. Astronomy is in a very exciting time. It is truly about to become astronomical in scale. From telescopes that spread across countries and even continents, to data and facilities that take generations to plan, build, and use. With all of these new telescopes that are coming online, which we'll hear about today, astronomy is about to embark on a new era of big data when the flood of information from the heavens overwhelms us, where no human will ever actually look at that data. Instead, we will trust algorithms, computer programs, AI, to spot the interesting things for us and let us know. And if we're not flexible enough, well, then maybe we'll never be told that there's something unexpected out there. Now, this afternoon, I'm joined by four incredible astronomers who are using the next generational telescopes of Australia, as well as its existing world-class facilities. We will cover those facilities that use optical light. That's what we can see. We'll range to those that use radio waves, which is what your phone can see. We'll explore the worlds and universes that are created on supercomputers, these simulated universes, and compare those against the real universe to understand our theories better. And then we'll have to tie it all together with a new scale, a new way of exploring the data, both the real and the simulated, as part of a worldwide virtual observatory. It's an exciting time for astronomy, with huge unknowns, incredible challenges. But here's the thing, you don't actually have to be an astronomer to be part of this. To make the next generation telescopes possible, we don't just need astronomers. We need computer programmers. We need electrical engineers, civil engineers, statisticians, tradies. We need government and industry on international scales to take part in designing, building, and making real the new telescopes that are coming. And with these new facilities, we can explore the universe in incredible new ways. Now, this afternoon, I'd like to start our talks in something that's a little bit more familiar. It's what you can see in the visible light with Dr. Angel Sanchez-Lopez from the AAO and Macquarie University. Please welcome him to the stage.
Thank you very much, Alan. Thank you, everyone, for being here. It is a real pleasure to be starting this presentation with what we are doing at the Australian Astronomical Observatory. So I'm a research astronomer at the Australian Astronomical Observatory at Macquarie University. So let me first show you that the majority of the information that we get from the stars, from the universe, it is coming in the light. But to observe that light, we actually have to dim our light. We need the darkness of some places just do not have light pollution at all in order that we can see the very faint light from the stars and very faint and distant galaxies. So if you can please dim the light a bit from here, hello, dim the light, you will be able to see much better what I'm trying to tell you today. So that is our Milky Way, our galaxy. scenes from Sidon Spring Observatory, which is where the Anglo-Australian Telescope and some few other telescopes at ANU, the Australian National University, are located. That is the huge dome of the largest optical telescope in Australia, the Anglo-Australian Telescope, 4-meter telescope. We want to understand what is happening with the light of the stars. For doing that, we need to collect the light. So astronomy is very different to other science in that sense. So we do not do experiments. Well, we do the simulation that Luke will be talking later. But we have to be collecting the light passively and taking the light in order that we can detect this faint scene. But the main important part in astronomy, again, they are the stars. So that is the sun. It is an image of our sun. I want to emphasize as a star, it is just a giant kitchen. It is just, you have hydrogen and you are creating other elements. So it is creating for hydrogen into helium. But I'm not going to talk about that today. I just want to show you the comparison of our sun, which is 700,000 kilometers wide, with the Earth. And you may think that the sun, it is big, and it is big for us. But it is actually not that big when we compare with other stars in the universe. So if we put the sun in that kind of a scale, there are other stars that are much larger than the sun, much bigger. There are blue stars, supergiant red stars, and a plethora of many different kinds of stars, even very dwarf, faint red stars. So the funny thing here that we astronomers were able to understand during the last century is that we can organize this in a very nice way. So we have the brightness in the vertical axis and the color in the horizontal axis, and there is some kind of evolution and sequence. So we have brightest blue objects that are very hot, while the red objects are very, very cold. So just using colors and using the brightness, we can actually start understanding and collecting the data to what stars are. And galaxies are collections of millions, of hundreds, thousands of millions, billions of stars. Some of them are elliptical galaxies in the sense that we only see a kind of elliptoid shape, red colors, meaning that they are all stars, the majority of them, while other galaxies, such as spiral galaxies, they usually tend to have these blue colors, and blue colors are revealing the giant stars. So we can put that in context in data and say that a file containing just the brightness and the colors of one star of one galaxy, it is only 100 bytes. So it is not that much. So not that much. With a DVD, which is the scale that I'm going to use for you today, 4.4 gigabytes, a DVD of data will have the information of 47.3 million objects. But that is only just collecting the colors and the luminosities. We are going to go deeper, because let me show you another important thing in spiral galaxies. All these reddish colors that you see here, they are actually star-forming regions. They are nebula in that galaxy in M74. So we have an example here of the Eagle Nebula, and the light coming off also from the nebula, it is very important for us. And I want to say that the light is actually, the gas is actually growing because of the effect of the massive stars. So these stars have been born inside the nebula. That is just using an image. If the red color, it is coming basically for the hydrogen, which is a diffuse gas within galaxies. We can use special filters to see the nebulas and the galaxies in a different way. For example, this here, and it is just a completely different way of understanding the universe. So if we actually go deeper into the detail, we need more than colors. We actually have to analyze very carefully the light coming from stars, galaxies, and nebula. Imagine that a star. If you take the light of that star and you use a prism and you get the rainbow, all the colors of the rainbow, you actually have something that the astronomers and physicists call the spectrum of the star, or the spectrum of a galaxy. And if you put here a lens and you get the information there, you will see that it is not a continuum of the light. There are some black lines, a code bar in the light coming from stars and from galaxies, and these are related to the chemical elements within those stars and without those galaxies. So codifying all those lines, codifying all those absorptions of elements, it is also very important in order that we do the physics and we try to understand what is happening in galaxies and stars. So that is what is happening. I mean, that is when we use a star. That is the kind of light spectra that we have. But for a nebula, that is a very different thing. As I told you, the light of the gas is actually emitting a lot of light, but emitting light in very particular lines that are the emission lines. For example, that one, this bright one, it is oxygen, and that is why you are seeing with these special filters, with these special images, you are seeing the colors so nicely. Of course, we astronomers, we do not want to see this very nice image. We tend to do something like this. Don't be scared. Don't be scared. It is just a cat saying, well, the color or the wavelength, which is the physical property, and in the vertical axis, the flux, how much intensity you have. So we have all these lines of hydrogen, helium, sulfur, oxygen, iron, just name it. And that is the way we know the composition, the chemical composition of stars and galaxies, even though they are very, very far away. So what we have been doing for a lot of time, at least until the late 90s. So we have the field of galaxies. Right? We'll go take the spectra of the galaxy, be there collecting light for 20 minutes, half an hour, and with that, we have a look to all these lines, emission and absorption from the stars and galaxies, and we can determine the distance where the galaxy is, how many young stars, how many old stars, the chemical composition, the age, plenty of more information that I'm not going to go into detail. But just a single of these spectra will have 200 kilobytes per galaxy. Imagine that we are doing that during a lot of time for just taking your telescope, pointing there, taking the light, go to another galaxy, and so on. That is what we were doing till the 90s, and we get around 10,000, sorry for that, around 10,000 galaxies. But Australia and the Australian Astronomical Observatory have developed really powerful instruments that are able to do much better. That is the 2 degrees field, or the 2DF instrument at the 3.9 meters Anglo-Australian telescope, which is just a plate more or less this size. And in that plate, you can put 400 optical fibers in the position you want in order that you can observe at the same time 400 objects in the sky. So typically, we observe 360 galaxies at the same time. So in a good winter night, we can get even 3,000 objects in a single night. That means that in only 4 nights, 2DF is able to observe the 10,000 galaxies that I told you that took decades for other telescopes to get. Thanks to that was commissioned at the end of the last century. We completed the 2DF Galaxy Redshift Survey, 2DF GRS, in 2002, and that is the actual three-dimensional distribution of galaxies far away that you can see in the diffuse large scale of the universe, how they are connected by filaments and some condensation of galaxies. And that was the depth of 2.5 billion light years with 230,000 galaxies. So that data was only 44 gigabytes of data, or equivalent to around 10 DVDs. But we are just starting, because after that, we have been completing more surveys, that most of these optical surveys go even deeper and deeper in the universe. That is one of the most important ones, the Gamma survey, the Galaxy and Mass Assembly at the AAT. So we completed, it was completed in 2013, more than 300,000 galaxies observed. That is again a distribution about a very particular part of the field of gamma, the 5 gamma fields. And we use actually a new spectrograph, a new thing. So we were getting a megabyte per galaxy. So that were at the end around 71 DVDs just to contain the information that we got of all these galaxies. 2DF, this very interesting instrument at the AAT, can be not only used for galaxies. We have been also using that for stars. But for stars, we actually need a bit better resolution, and that is why we built the Hermes spectrograph. And we are now conducting the galactic archaeology with Hermes, the GALA. Here you see the GALAs observing at the Anglo-Australian telescope. That again the aim is to get around 1 million stars in the Milky Way and in the Magellanic Clouds, just trying to understand their evolution and how the galaxy, our galaxy, the Milky Way, have been assembled. So just that, around 2 megabytes per star, so equivalent to 442 DVDs. And we are going there, still telling you, because that is okay for galaxies. So we are taking just a spectrum of a galaxy, but if you see an image like this, M51, the Whirlpool galaxy, and you put and try to get the spectra of just getting one particular position of the light, well, that is not the galaxy. So you can go to the center, you can go to the other one, to another H2, the other star-forming region. So we actually need new instruments to go deeper into the understanding of the galaxies. And that is why we have developed in the last decade this kind of structure that it is actually not taking a single spectra of one galaxy. It is taking hundreds, thousands of spectra of galaxies. And it is called the technique integral field spectroscopy because it is just doing the integral field. And it is much better seen perhaps with this image in which at the end what we are not collecting, we are not getting, it is just a spectra. We are getting cubes of data. And it is very, very, very interesting just to try to see moving around those cubes and trying to get the visualization of all of that because it is really tricky and it has a lot. We need a lot of computer power. So we have 10 to 1,000 spectra per galaxies. Perhaps the very first survey doing something like that was the Khalifa survey, which we conducted in Spain with a Spanish telescope. And around 500 megabytes per galaxy, 700 galaxies. So at the time, we only have 78 DVDs. Well, again, you go to your galaxy, put your instrument there, and just wait and collect the data for several hours. We need to do something a bit more better. And that is, again, why we are pushing the technology. And we at the AAO and with the Sydney University, we have built this new instrument, which is called SAMI, the Sydney AAO Multi-IFS survey, that we are not only getting the data in that way for one galaxy, but for 13 galaxies at the same time. And every one of these have this kind of bundle, and with the spectral field of the galaxy. Every one with 51. That is me at the telescope just a few months ago, actually doing this because the thing is that we have to do it manually. It is the thing. But we have already 1,800 galaxies observed. We aim to get 3,000 galaxies, and we will get 22,326 DVDs. And I think that wait for it. And I think that wait for it because at the same time the AAO is developing the Taipan survey to be installed now in August, September at 1.2 meters UK Smith telescope in Silent Spring, and that has the system that is called Starbucks. And these Starbucks are actually moving around, and it is just, you do not have to go and plug. It is just a computer that is able to move and put everything together in just some few 30, 40 seconds. I'm not going to give you too many details about that. It's going to do stars and galaxies at the same time, and we are going to get around 666 DVDs because they are just fibers. It is just testing what we really want to build, which is Hector at the AAT, which is just a system that is able, where it is coming, please? That we want to observe 100,000 galaxies using the bundles, and then we will get only for one galaxy 5 gigabytes of data. So that will be the equivalent to 113,636 DVDs. What do you think? Come on. Wow. We go directly into the Star Wars, into the galaxies. We will get unprecedented statistics for understanding the galaxy's properties in the local universe. And let me just give you this last number for finish. Just the AAO telescopes have provided 1/3 of all the redshift of the galaxies that the humanity has right now. And that has been thanks to the technology and to the astronomers that we have at the Australian Astronomical Observatory. Thank you very much.
All right, thank you, Anna. So I should point out, we will have a Q&A at the end, and you get to ask all your questions. If you can't wait, you can tweet us right now, tweet the scientists at #SolVividSydney. So Sol is the name for the sun, or the story of light, as a clever acronym. As you might have guessed, astronomers, we do like our acronyms. So SOL, Vivid Sydney, and we'll kick off the Q&A with some of those tweets, and then we'll go old-fashioned and use the microphones and get the audience to participate directly. So now we move from the optical, so what we can see, to the truly amazing world of, well, the invisible, at least for us humans, at least until we built radio telescopes. And no place does it better than the ATNF, and we're joined by Dr. Vanessa Moss of the ATNF to tell us all about radio astronomy. Please welcome her to the stage.
Okay, hi everyone. So my name is Vanessa. I'm part of the University of Sydney, part of a research centre called Castro. We work very closely with CSIRO to work on radio astronomy and really see what we can see far off into the universe in wavelengths, like Alan said, that we can't see with our eyes. So today I'm going to give you an insight into radio astronomy and why it's such a big deal at the moment here in Australia. So if we go back to the image, something like what Angel was showing, so we might dim the lights again maybe, and this is something you might be familiar with if you go outside with your eyes. So you look up and you see the stars up in the sky, you see the Milky Way maybe stretching across. We're actually very lucky in the southern hemisphere to see the Milky Way so clearly. If we zoomed in on any one of those individual dots, we might expect to see a star, something like this. So every little dot here is a star. However, if we were to put on our radio goggles and instead see the sky with radio eyes, this is something like what it would look like. But instead, every single dot you see here is not a star. It's much more likely to be a whole galaxy far, far away, hosting a giant black hole at its center. So even though at first glance it looks quite similar, it's a very different view on the universe. And they're big, these galaxies. So this is our nearest radio galaxy, a galaxy called Centaurus A. You can see it at its scale on the sky. So imagine if we could see this with our eyes, it'd be really cool. So that's the moon over to the left. So if we could see Centaurus A, we'd see it stretching across the sky, huge. And that's just our closest one. So and this is, in reality, Centaurus A is only this big because it's so close. If we could zoom in on the other galaxies, they're even bigger. But it doesn't stop there. Radio is one part of what we call the electromagnetic spectrum, so that rainbow, but extending it to both low energy in the radio and high energy with the gamma rays and X-rays. And the important thing to take away from this image, each of them is showing you a picture of the Milky Way, our home galaxy, is that we're tracing different physical processes, from electrons in magnetic fields to high energy particles tracing collisions in very hot plasmas. So the physics is what's important when you look at different wavelengths. I'm going to introduce you to my favorite atom. Some of you might look at it and instantly recognize the hydrogen atom. This is a proton with a single electron orbiting it. And it's the most fundamental atom in the universe, and it's found everywhere we look. This is a different way of representing it. So you have the proton in the middle. The electron kind of doesn't just stay in this nice orbit. It can be found in lots of different places. That's where we overlap with quantum. And the blue sphere is representing the places that you could find it. So it's this weird thing. It's not this static shell where you have a proton and electron. It's more complicated than that. And it turns out if you have a lot of hydrogen just sitting out in the universe, not doing much, very, very occasionally it will have what we call a spin-flip transition, which is just it sitting there going, okay, flip. This happens very rarely. You can see once for a single atom, once every about 6 million years. But fortunately, there's so much hydrogen out there that we pretty much see this transition everywhere we look, both close to home and very far away. So this is showing you, roughly, if you could see, instead of radio, specifically hydrogen in our sky. The disk, like the line across the top, is showing you the hydrogen disk of our Milky Way, where the stars are, so they kind of overlap. Those two little blobs down the bottom are our two nearest galaxy neighbors, the Magellanic Clouds. So again, you're seeing a different part of our universe. You're seeing this time the gas that the stars form from. This is a different way of showing it. So this is all of the hydrogen in the southern hemisphere. This image or this survey was made with the Parkes telescope by my supervisor, my thesis supervisor, Naomi. And so she spent a lot of time on this, getting all the data for the sky, showing you the disk of the hydrogen going along there, so that's the Milky Way, as well as this interesting rainbow structure here. So this is the Magellanic Clouds, and the reason they show up as rainbow is because the color here is showing you the speed of the gas. What we know now is that the Magellanic Clouds are orbiting the Milky Way. They're in the process of merging with us. So hydrogen, because it has a velocity, you can measure that. It gives you a unique perspective on what the gas in our galaxy is doing. So last weekend, I thought I'd make a little movie to try and show what that image is. You think of every single slice here as the gas at that velocity. So this is the speed down the bottom. So at high speed, there's not a lot. This is because it has to be moving very fast towards or away from us. As we get down to the low speeds, this is showing us the hydrogen that surrounds us in our spiral arm, so there's a lot of it. And at high velocities, again, you can see the Magellanic Clouds coming in because they're very different to the rest of our galaxy. They're not part of it yet. And so that's why they stick out so much. So just let that run. And at the end, if you stack all that together, you get this image. So that's how that is made. Our galaxy, we think, is pretty peaceful. I mean, we are here. We've been here for a while, and our solar system is relatively stable these days. But there's evidence to show that it wasn't always so peaceful. So if we look towards the center of our galaxy, at the black hole, the supermassive black hole there, you can actually see evidence for very high energy bubbles. So what that tells us is that maybe not so long ago, the Milky Way was a little bit more like the galaxies we see far away. Its black hole wasn't just sitting there being kind of quiet, it might have been spewing out material from the center, which is not really good for life if you happen to live near it. So understanding the connection between our galaxy and the other galaxies we see in the universe is really important because we want to know where we fit in to this global or universal picture. In Australia, we have a few different tools at our belt for this. This is the iconic Parkes radio telescope. It's out in Parkes, not surprisingly, and it's 64 meters across, so it's huge. It's most famous for its involvement with the Apollo missions, but more recently, it's been the leader in the discovery of a new phenomenon called fast radio bursts. The Australian Telescope Compact Array is a little bit different, so instead of 64 meters, you have 24 meters, so they have a bit of a different view. These telescopes live on a railway track. So you can move them up and down this railway track depending on what kind of science you do. And a lot of the science I've done in the past has been spent at this telescope, observing everything from supernova remnants to high velocity clouds. Down in Canberra, there's a complex called the Canberra Deep Space Communications Complex. So this is a combination of CSIRO working with NASA. These telescopes spend most of their time talking to rovers and satellites that are traversing the solar system. So they're having a chat, sending data back and forth. And there's 4 operational telescopes, including the biggest single dish in the southern hemisphere. Southern hemisphere? It's probably still true, at least in Australia, the 70-meter Tidbinbilla telescope. So it's actually 6 meters bigger than Parkes, slightly bigger. So that's down in Canberra, and there's 4 operational telescopes there. Just wait for that to load. So a relatively, maybe I didn't click it. A relatively new addition to this bunch of radio telescopes is something called the Murchison Wide Field Array. This is out in the Murchison Desert, which I'll talk a little bit more about in a second. Looks very different to the kind of telescopes you've seen so far, but it works in roughly the same way, just at lower frequencies, so the antennas are getting the radio frequencies. And they're often referred to as spiders because of their shape, so they're pretty cool. And now I'll introduce you to the Australian Square Kilometre Array Pathfinder. So while that's playing, so you can see that it's a very, very dark site. The reason we go here is because not only do we need to be far away from, people, but we also it's like optical, right? You want to go somewhere very dark because of light pollution. But in radio, people's phones, their microwaves, they interfere with our radio telescopes in the same way. So if we want to probe the universe at a level that we've never seen before, we could either build it on the far side of the moon, which is really tricky, or we need to go to a very, very unpopulated place. so that we're not going to have interference from all of our radio communications getting in the way of these telescopes. So that's why it's built in such a remote area. It's actually still in the process of being built. There will be 36 dishes total when it's finished. And we're currently at the stage where the first 12 all have their receivers on them. And they're testing them so that we can get started with science surveys by the end of this year, we're hoping. So this is super, super exciting. This is just to give you an idea of what the place is like. So it's built on a station called Bilardi Station. This is Monty, the station family's dog. And he wanders around and is super friendly to astronomers. So it really is the Outback. It's a very different area to where we've built radio telescopes before. It's super remote. It's about an hour north of Perth by plane and then 3 hours inland from Geraldton. So it's pretty far. And this is what the telescopes look like. So they're scattered across several kilometers. This is a photo I actually took last weekend. Usually it's super dry out there, but recently we've had a little bit of unexpected rain, so that's why you see water. So some of them are close to each other, some of them are far away, and altogether they work as one telescope. The thing that really sets these apart is something called a phased array feed. It's that circle you see at the top there. Usually what you'd see in a telescope is just one pixel, sort of. But this is a big circle of lots of pixels. So if we zoom in on that, you can kind of think of every gold square here as a pixel. So similar to how Angel was showing, we used to get one spectra. Now we can get lots of spectra at once. And so the idea here with radio astronomy, we always kind of got more spectra at once, but we can see a lot more of the sky at once. So it makes surveys much, much quicker. And it's very cool too. Super cool technology. So to give you an idea of what a PAF sees when it looks at the sky, this is a very early image while it was still being built. And that's showing you the part of the sky that it sees relative to the moon. So this is the real part of the sky, so it's huge. Every little blue dot is a galaxy. If we zoom in on one particular galaxy, which is a very cool one, then we suddenly have access to 4 billion years of universe evolution in hydrogen. And if we look closely at this kind of data, we might be able to find a new galaxy. And this galaxy, you might be able to see it, the little blip there, was actually the first discovery made with ASCAP while it was still being built. So this was pretty exciting. A different way of showing you how big the data is, so this is when I printed out the spectrum on a long, 40 pieces of paper and stuck them all together with sticky tape for a demo. It's about 10 meters long, and if you're curious, it took 9 kids to help me hold it up at Google. So that's a different way to show how big the data is. And the little red thing you can see, that's the actual galaxy. So we have a lot of data to look through. But how big is big? So, how big is the data actually getting? So to give you an idea, what I've done is assume that we're going to take a data in an hour from a telescope, burn it to a CD, and then stack those CDs of 1.2 millimeters each in a little pile and measure how high it is. So if we do that with a compact array, we get about 12 gigabytes an hour, which is about the size if you put a 5-cent coin up like this, or the size of your thumbnail, so it'd be that high, not very high. A big telescope in the US, the Karl Jansky Very Large Array can do a lot more data. That's like its maximum rate. And this would be about a CD stack of 10 tuna cans high. I measured it last night. Tuna cans are about 3.5 centimeters. So anyway, so tuna cans, I don't know, 35 centimeters is a bit of a weird measurement to come up with. If we go to this Australian Square Kilometre Array Pathfinder, so this, obviously it's not built yet, so we're still trying to figure out just how much data we're going to get. But as we progress in technology, as it's being built, it's likely to get bigger. So one data rate might be 36 terabytes an hour. So if you burn all those to CDs, you'd get something the height of the Opera House. So you can see that there. But the Square Kilometre Array Pathfinder is a new era. So if we took one of the estimates from the Square Kilometre Array, which is the next generation of telescope we're going to, that's what ASCAP's being built to test, to lead the way towards as one of the many Pathfinders, then it's going to get something like 100 terabytes a second. So think about that, right? 100 terabytes a second, that's ridiculous. We're going to need to cut that down because even with Moore's law and all the different technological things we know, we can't deal with 360 petabytes an hour. So if we stacked all those CDs up, it'd be roughly the orbit of the Hubble Space Telescope from Earth. So you can see we have huge technical challenges to think about as we move into these new telescopes. So hopefully you can see that we're entering a phase of many new astronomical challenges and technical challenges. And it really does feel like the dawn of a new era for radio astronomy, particularly here in Australia. And we don't know, when we point these telescopes up at the universe, we don't know what we'll see when we have more sensitive radio eyes than ever before. And I think that's what makes it one of the most exciting things of all. So, thank you.
first tweet, so thank you for that IQQI Backtal6. I think I got your handle right. So again, hashtag is Sol ViViD Sydney to ask your question and beat the line for the microphones. We now go from the visible, the radio, and now firmly into the realm of the theoretical. This is something I have a bit of love for, and I'm super excited to hear from Luke Barnes of the University of Sydney, who will be describing the efforts we go to make galaxies, make universes, and explore them better. Please welcome to the stage Dr. Luke Barnes.
Thank you very much, Alan. As Alan said, this is a personal love of his, so if you have any particularly difficult questions, feel free to ask Alan. So the alternative title of my talk is Making Universes for Fun and Profit. I'm Luke Barnes, as we mentioned. So I want to start with a question that a theorist might ask. It's a little question like, why are there galaxies? There's a good start. Particularly, what are the processes that make galaxies? Can we understand those? So how do you even get started with a question like that? Well, the way we get started, there was a great tip from one of the great physicists of the last century called Richard Feynman, who gave us this little tip. It is not unscientific to make a guess. We start by guessing, and it really is guessing, but it's constrained guessing. So we know how the stuff in the universe behaves. We sort of understand from studying the solar system how gravity behaves. We understand how matter behaves in certain situations. And so we can start to have a guess about how the universe might work. So for example, here's a guess that we made sort of in the 70s and 80s. It's just a story, and then we try to see whether we were right. That's when science happens. So here's the story. Maybe the universe started out very flat and smooth, but there were small lumps of matter just with a higher density than average. And then the main player in this story is gravity, right? Gravity is not egalitarian. Gravity makes the rich richer and the poor poorer. If you are a big lump of matter, you will attract more matter and make yourself into an even bigger lump of matter. Okay? That's how gravity is going to work. It will do that until something starts to fight back. And in this case, the thing that fights back is gas pressure, the stuff inside a balloon. If you try to squish a balloon, it will fight against you. So the next important thing we need that gas pressure actually to give way. We need something to leak that away, because galaxies aren't just big balls of gas held up by the pressure. They, as you've seen, they go around, they swirl. So gas cooling is the second part of our story. Gas cools by emitting light, that light escapes, and that gas is less able to fight gravity. The third thing that will happen is once the gas gets into a disk, it will start to form stars. That stars will start forming into a feedback loop. You have a loop. Loop. That's my name. That's why that was funny. Feedback loop. If it was named after me, that would be amazing, but it's not. I can't claim that. So you have a nice little cloud that makes a star. It's got lovely conditions in there, but then you've made a star in there, which is going to pump a whole heap of energy and light into its surroundings. It's going to push things away, and the big ones blow up, which isn't going to do very well for the cloud. So it will disperse the cloud, but then clouds will form elsewhere, making more stars. So things will go around in a loop. That's the basic story that started coming together in the 70s and 80s. So the question is, how can we test that idea? So here's where we'll start. We'll start with the universe's baby pictures. This is what the universe looked like when it was very young. This is our starting point. Okay? We need to turn this into galaxies. So this is a picture of the night sky at a certain wavelength, which reaches right back into the beginning of the universe, and it shows that the early universe was very smooth. That smooth beginning that I talked about. This is the whole sky. What you really need to do with this is wrap it around your head, thusly. Okay? Now, once you've got that, we sort of know how to start off our simulation. We're going to do this in a computer. Now, what we would love to do is just represent every particle out there in the universe, and then press play and watch the universe happen. That would be fantastic. Unfortunately, not really feasible. Okay? Every lungful of air that you have, if you wanted to write down the number of particles in that lungful, you would need about 23 digits. Okay? So we're not going to do that in a computer for an entire universe. What we use are tracer particles. So, for example, this is a wind tunnel. The air is flowing past, and then you put, say, smoke into that air. and there'll be much fewer smoke particles, but you can actually see those and they will trace the air. So as you see there's a little swirl of smoke, you know that the air there is swirling. Okay? So what you're going to do is we're going to use tracer particles. So we have what's really just a list of particles, and their positions is all that means in the computer, right? So we'll just lay down a whole heap of particles in our computer, which is just a list of numbers. We know how gravity works, so you can take each of these particles and say, okay, it weighs this much, it's this far from that particle, what's the force on it? And then the next time step, you give it a little kick in that direction. That's how gravity works. Not literally with kicks, but close enough. We know how it will cool if we keep a track of its temperature. And then when it's a certain density, when in certain conditions, we can make stars and do all sorts of things like that. But in the computer, it's just a list of numbers. You know, its position, how it's moving, its temperature, all those sorts of things. You could do this in a spreadsheet. However, I can't stress this enough. Don't. Because we're using roughly 1 billion, maybe 7 billion particles here. So, for example, one of the world-leading ones of these is the Eagle project based at Durham University in the UK. They have 7 billion particles, and you're trying to trace out the entire history of the universe, so it's going to take you a while to do that. So, if this computer were to try to do this simulation, not using all those computers, and you wanted it done in an hour, you would need to have started it during the reign of Henry VIII. So don't do it with one computer for 500 years. Get 4,000 computers to do it in a month and a half. And then hope that nothing happens in that month and a half. Okay? I once opened up my email to find an email from the National Computing Infrastructure, which included the words vaporized, and was describing the power source for their supercomputer. So that one went down the drain. Never mind. After that month and a half, you'll have about 500 terabytes of data. I haven't converted that into a number of DVDs, but that's 500 of those hard drives, just full. What we need to do with that data is visualize. We need to get amongst it somehow to see what's going on. So what we can do is, we have sort of a map of all the stuff in the universe over the entire history of the universe. We can put our sort of camera in there and have a look around to say, what would it look like? We could light up the gas depending on how dense it is, or perhaps on its temperature. And we want to see what's going on here. And one of the great advantages of this is that it makes very, very pretty movies for us to show. You'll start to see gravity winning. So anywhere that's dense starts getting denser. And in particular, if you have a blob of gas, it will collapse along its shortest axis into a sort of pancake. Then those will collapse into filaments, and those collapse into knots. And then up starts the star formation feedback. Those stars are starting to blow up and push hot gas back out into the universe. So it's pretty good on the screen here. It's very good on this screen here. You really owe yourself, these are all available online. Sort of a quiet room, a dark room, an afternoon, some scotch, Beethoven. Get amongst it. So, we need to answer our question, did we make a galaxy amongst all this? This is a sort of big scale view of what's going on with the universe. It's nice to see that sort of filamentary structure we saw before. Did we make a galaxy? What we'll do now is we'll send our camera in nice and close on somewhere that hopefully looks like a galaxy and see what happens. Okay, so on the left, same sort of picture but zoomed right in. Temperature again. On the right is what astronomers call metallicity, which is basically all the stuff that stars make. So this is not the original gas, this is the stuff that got processed inside a star and then blown back out into the universe. But as you can see, as stuff starts coming in and it's cooling, the thing that stops it collapsing further under gravity is its rotation. So that's what's stabilizing the system here as it starts to sort of suck up all the little pieces. Not bad. So it's looking a bit like a galaxy, but there's so much detail in there. We need to know how to compare this to data. So one thing we can do to compare it with data is to look not just at where the stuff is, but how it's moving. So to understand this, to compare it to data especially, I need you to understand the Doppler effect. So as an ambulance drives past, it goes, meow, right? So if you had, say, a skier going down a mountain with a trombone, oh, why not? he has a video of him going down a mountain playing Ride of the Valkyries. All right? Beautiful. I watch that probably once a week and just giggle. Right, so here's our little piece of a galaxy, and what we want to do is light up, colour it according to which bits are coming towards you and which bits are going away, to not look at where the stuff is, which is what that is, but how it's moving. And so when we do that, we get this sort of picture. So on the left there, the blue, because it's coming towards you, the light appears at a shorter wavelength, bluer light, and on the right is the red, the stuff going away from you. So if galaxies consisted of skiers with trombones, the left side would be going ba, and the right side would be going ba, okay? We can see that in our simulations, and we can go and compare that to data. So Angel mentioned the SAMI Redshift survey, when they were, galaxy survey, sorry, when they were very excited because they had 700 galaxies, they've now got 1800. They put out this picture, and you can see these are all galaxies, and you see that same pattern. Blue on one side, red on the other, that rotation. One side's coming towards you, one side's going away. So that's all particularly exciting. So that's one of the ways we can get information out of these things. But there's so much information in there, we've really got our work cut out. As I finish with another lovely image, let me just mention, if you want more details about how galaxies form, plus how the universe expands and its fundamental forces and alternative rules for chess and life for the universe and everything and entropy and all that sort of stuff, then I can highly recommend a book I have coming out this year with Geraint Lewis from the University of Sydney called A Fortunate Universe, Life in a Finely Tuned Cosmos. And I will let that video play out and say thank you very much for listening.
Thank you, Luke, and thank you for that shameless plug. Well, all of the effort you've heard today, from optical to radio to making it up, all of that data would be for nothing without our next speaker, Dr. Liz Mannering of the AAO and the International Centre for Radio Astronomy Research in WA, or ICRA. Basically makes our jobs possible by storing, sharing, and further understanding all of the torrents of data that we've been taking, and I hope is braced for the next generation torrent of data, which, as we've heard, will stretch all the way into space. So would you please welcome to the stage Dr. Liz Mannering.
Hi everyone, I'm Liz. We'll step back a bit first and we'll kind of think, what does your typical astronomer look like? So you might picture an astronomer as a lone scientist, so plotting the positions of stars and galaxies in a notebook, staring up into the cosmos. And 100 years ago, this was how astronomy was done. In 1923, Hubble made the discovery that there was more to the universe than the Milky Way. So he observed the changes in the brightnesses of stars in these fuzzy nebulae that people thought were within our own galaxy. And he showed that these fuzzy gas clouds were actually 10 times further away than the furthest stars in our own galaxy. So they were in fact galaxies in their own right. So the Andromeda Nebulae here was renamed the Andromeda Galaxy. And this is one of the photographic plates that Hubble took at the Hooker telescope in California. And the amount of data here isn't very much. It's about 50 kilobytes worth of data. So he managed to change sort of our view of the cosmos with the amount of data, less data than an audio track on your MP3 player. So as time went on, engineers and scientists constructed sort of bigger and different sorts of telescopes. In the 1950s, radio astronomy took off, and as Vanessa talked about, we had this huge boom in discoveries. A new type of galaxy was discovered, the radio galaxy. And in the 1980s, the focus of astronomy research turned to deep space observation. So engineers and scientists began launching telescopes into space to overcome the interferences of our own atmosphere. And they could now capture UV, X-ray, gamma rays. And those different wavelengths revealed a whole new picture of the universe. So you can see this is Centaurus A. If we only had the optical image of this galaxy, we'd be missing all of these other processes that are going on. So scientists could work together now in small teams, and they'd use computers to process and analyze this new wealth of data. So bigger, faster and more sensitive telescopes are being built. Astronomy booms with this new flood of data. And they started using telescopes to survey the sky and collect images of millions of stars over several years at many different wavelengths. Data sets then became an order of magnitude larger and more complicated. So the age of the mega survey had begun. So this is an image, well, it's a snapshot of a few galaxies from the hugely successful Sloan Digital Sky Survey. And they had their first data release back in 2000, and they released 3 terabytes worth of data to the public. Now, if you tried to download their data volume back in 2000, it would have taken you 14 years to download on the current internet speeds then. But luckily, they provided astronomers with a web form. So an astronomer could say, well, I only want that particular piece of the sky. Give me the data for those galaxies. So astronomers could use the internet to start accessing bits of data that they wanted. And this meant then that astronomy sort of started becoming collaborative across the globe. People could work on a problem across the world. They didn't need to be in the same room. So the Gamma survey that we saw the fly through earlier is actually made up of over 100 different astronomers working at a dozen different institutions, using data from 10 different observatories, over 21 different wavelengths, studying 250,000 galaxies. So we've seen astronomy change from single source, single wavelength, single astronomer, to multi-source, multi-wavelength, multi-astronomer. And we've also seen that astronomy data is really most useful when it's combined with other related data. And this is where virtual observatories come in. So virtual observatories make all the data that's available online easy to access. In the same way as a real observatory contains a unique collection of instruments, telescopes, virtual observatories provide unique data sets and sometimes analysis tools for accessing those data sets. So astronomers can then access all the different bits of data that's spread all across the globe and combine it with their data and make really interesting new key discoveries. And this is kind of where astronomy is going. So what are we building at the AAO? Well, the AAO has a wealth of data that is currently dispersed on loads of different machines all around the world. And we're building a data archive that not only stores that data, but allows other users to explore it as well. So by putting all these data sets into a repository, we make sure that they kind of get a new lease of life. They don't just get looked at once and then just die on some old machine somewhere. They're available for other scientists to play with. So we're starting with the Gamma and the SAMI surveys, which we heard a bit about before, and they're together about 15 terabytes. So this is the web page that you'll be able to go to. So you could download all the data that we have available, but even in this day and age, 15 terabytes on a 2 meg connection, you'd be looking at 3 months to download all that data, and you'd probably throw most of it away. Perhaps you only want, you want galaxies that live in a cluster, or galaxies that are isolated and just live on their own. So it's important that we build like a queryable interface to that data, so that astronomers can say, well, I only want this type of data, only give me data that looks like this, so that we can hand back sensible data to them. Or you can just go to our node and flick through pictures of galaxies. You can be on your morning commute, it's mobile compatible, and you can just flick through images of galaxies billions of light years away. So we'll have a public data release of that, I think, early July. But the AAO Data Archive isn't the only virtual observatory in Australia. We're part of the Allsky Virtual Observatory project. And that brings together data from radio telescopes, theoretical simulations, and optical telescopes through virtual observatories that you can then access with a web browser and an internet connection. So TAO is a free online mock galaxy factory, and that draws on the power of Swinburne's supercomputer. So as Luke said, you need a supercomputer for these things. So you can set your initial conditions for the universe you would like to grow, add in some parameters for how you'd like your galaxies to evolve and grow, and TAO will create you your own custom universe. So that's pretty cool. So the Skymapper node, the Skymapper Virtual Observatory, will provide a web portal to query and explore the Skymapper data, and that's a detailed digitized map of the southern sky at optical wavelengths. So some really cool images will come out of that. So the ASBO project is threefold. It's about getting data online and easy to access, but it's also about making all of our interfaces talk to each other. And that's a really powerful tool. So you can imagine that you would create a sample of galaxies from our node, the AO node, using the Gamma survey, say, give me all this type of galaxy. And then you could go to the Skymap archive and say, well, what do they look like on the sky? Give me some really cool optical images of those galaxies. And then you could ask Tau to search through its simulations for a particular type of universe and say, well, find all the galaxies that look like these galaxies in your simulations. And are all the other properties the same? Is that really how the universe works? So you can then tune your cosmological parameters in Tau until what you see matches what you really have, which gives you an understanding of the real universe. So that's where the real power lies, is combining these virtual observatories. So in Australia, we're actually part of an international project to connect all the virtual observatories in the world. So these International Virtual Observatory Alliance members either provide data sets or data access tools. Some of them will provide imaging, spectra, a variety of things. And the aim of this project is to get all of those things working as one seamless whole. So by bringing all these data sets online and connecting as many as possible to as many astronomers as possible, you can really maximize the scientific return on a project. So that means that the Webb really is the world's best telescope. So observations at all wavelengths are readily available for scientific analysis or just browsing around. You can be an astronomer and have never visited a telescope, which some people find sad. So astronomers and software engineers have created a vast global repository. And that repository might already hold some of the answers to the fundamental questions of the universe that we are asking. And if you want to go and play around with some of these tools and have a look at some real astronomy data, I'll leave these links up there so you can go explore them in your own time. Thank you.
Thank you, Liz. Has everyone taken a photo of this? Who wants a photo of it? Got 5, 4. We'll be tweeting out these links. As you can tell, Twitter really is astronomers' best friend. All right. Well, I think it's time we got to the Q&A. So if you could welcome back to the stage Angel, Vanessa, Luke, Liz. Please give them a warm round of applause. Okay, so we have a roaming microphone, but we'll just start off with our tweets. All right, IQQI84 for Iqbal. Loved the first talk. He hadn't seen any of the other talks when he tweeted. I'd like some numbers on the computational challenge to identify and track the millions of objects out there to process all this data. And that's actually something I'd like to we've sort of, Luke mentioned the scale of supercomputing perhaps, but if everyone else could maybe just briefly answer, what actually do you need to process this sort of data and what do you envisage in the future? Oh no, all of you get to. He's the one who has
I don't deal with that. I make my own universes.
Well, I suppose at our node we have to have sort of a really scalable system. So our cluster, our database, is kind of, you can think of it like Lego bricks. We've got it as big as we can for the amount of data that we've got now. I think it's about 100 terabytes we can take in. And when we need to, we'll start sort of clicking more machines on top to add in more data and more processing power. So at the moment, I don't know what our processing power is, but it's kind of very scalable. But it kind of depends on the code that you're running and how long you want it to run for, right? So maybe, Luke, you could give us an idea on the timescales?
Well, the simulation I mentioned, 4,000 computers running for a month and a half. But that's a very different sort of thing. We're simulating the entire universe for a couple of billion years. So to squish that into a month and a half isn't that bad, actually. But actually going and finding stuff in real data is another challenge entirely.
So I guess even before things like ASCAP and the SKA, we're already at the stage where our data sets are so complex that you have to be thinking about them in a different way. So it used to be that maybe you could make a plot and you'd look at it and you'd be like, oh, that galaxy looks weird, and then you'd follow it up and stuff. But now, because we have thousands, if not millions of galaxies, we have to think about the kind of questions we're asking, and it does go into a realm of statistics. So one of the new things, we have to think about things not just in probabilistic but also Bayesian things. So if someone wants to ask about Bayesian, but also machine learning.
Don't ask about Bayesian, please.
But so machine learning. So using computers to kind of help us make decisions about what's in the data when we can't see it because there's that many dimensions. So so it's complicated.
Okay, so I'm much more an observer than theoretical or doing what Luke is doing and what we have been presented here, but I can give you some numbers. So that is actually my own laptop. For getting, when we are observing for sunny, one of these single plates for 13 galaxies at the same time, we need to get, well, not going to visual details of where it's observing, but it is 3.5 hours in total observing in there, and getting around, that will be around 20 different files. To combine that together to do to prepare the data groups with that laptop takes an hour. Just for one plate. I think it is a good number.
Okay, that's pretty quick. So how many? So the next generation surveys have hundreds, thousands of times that scale, right?
Much more. We still need the supercomputers to do that.
Yep. So we're all linked by our love of supercomputers. So Parnian Khalidi, I hope I've said your name right, your Twitter handle right. How far does the visible borders of the universe extend at the moment, and could it extend further in the future? Oh, great question. So glad I'm asking them and not answering them. Anyone want to take that? Luke, I have a feeling.
45 billion light years. Ta-da! Sorry. So the question is really how far in the history of the universe can light have gotten? Right, that's how far you can see, in theory. If there's something in the way, obviously you can't see any further than that. So to understand that, we need to understand how the universe expands and what it was like in the past, and in particular, we need to know when that beginning point was. So thanks to the sort of the work that underlies our understanding of the way the universe expands, these sorts of simulations, the galaxy simulations especially, that number turns out to be about 45 billion light years. I said 46 billion light years. You'll notice it's not just the age of the universe in light years. The age of the universe is about 13.8 billion years. That's because it's expanding. So the furthest thing we can see is now further away, if you like. It's gone further away. So is it growing? Yes, at the speed of 1 light second per second, because you just wait a bit longer and you'll see something from a bit further away.
All right. Our final Twitter question was from FranzViz. Are there any crowdsourcing projects to help survey the sky? Galaxy Explorer, if you've not already done it, is amazing, but...
Oh, they're gone.
It's gone.
Yeah,
Yeah.
it's gone.
All right, I'll put the slide back so you get to take a picture, FranzViz. So Galaxy Zoo, Galaxy Explorer is the Australian version, so do that first, help us first, and then help the rest of the astronomers in the world. All right, and back again. Okay, so
for those surveys, I would like to emphasize another more, which it is a radio galaxy zoo, which have been developed between the ATNF, the CSIRO and ICRA, that is looking for the radio galaxies and trying to understand how the very massive black hole that Vanessa was talking about in the center of these galaxies, and if we are able to put the optical light in those galaxies to identify where they are, and it is called Radio Galaxy Zoo. Go for it because it is very, very nice to see.
Radio Galaxy Zoo. Okay, so we have a floating microphone. And has someone already got the microphone? I can't even see. If you have, please feel free to ask your question. There's one at the front, but I think someone actually has. Oh, yeah. Just say your name and please actually have it as a question. If possible, that helps if it's a question. All right.
Hi, my name is Matthew.
And Matthew?
Question for Luke about the simulations. Given that we still know relatively little about dark matter and dark energy. How do you account for the effects of those in your simulations at that sort of scale?
So we know enough about them to put them in these sorts of simulations. What we don't know is what would happen if they hit ordinary matter or if they hit each other. But we know gravitationally what they do, and the answer is not very much. So dark matter is, we know that there's more stuff out there than just the stuff that stars light up, or even the stuff that stars are made out of. There's something else there with a gravitational pull, but that isn't showing up, hasn't been seen down any telescope. So that we call dark matter. There's also something which, in our understanding of how the universe expands, is, for some reason, making that expansion accelerate. The universe is not just getting bigger, but getting bigger at a faster rate. We know that much, and that's all we need to stick them in these simulations. If they had these other properties, they probably would have shown up in our observations, but there are, if we knew exactly how it interacted with itself and with other matter, maybe that would make it, maybe we're missing something. So in particular, there's an Australian experiment that Alan is itching to tell you about right now. See how he's leaning forward? I don't even have to look at it. It's in my peripheral. Go, Alan, go.
Nice segue. Okay, so there is an experiment to actually find the dark matter. So we're actually, at the moment, flying through the cloud of dark matter that our galaxy sits in, and in fact its gravity is holding the Milky Way together. You've never felt this occasionally. It's actually flying through us right now, and quite literally there are these invisible particles. And I realize I'm not saying like a Scientologist or something, but there's this cloud of what we call dark matter that we're flying through. And very occasionally it will hit an atom in your body, and you'll never have felt that, I hope. If you did feel something, I can assure you it wasn't an atom being kicked out of your body. Oh. But the fact, someone got it. So this dark matter does occasionally collide, have a head-on collision with an atom, the center of an atom. And we're building a very sensitive dark matter detector and putting it at the bottom of a gold mine in Stawell in Victoria. And all that rock above will stop radiation from space, which would otherwise blind our detector. So that's stopping all the radiation, but the dark matter flies through it, completely unaffected, and very rarely will hit our detector and cause it to glow. So what we're looking for are this glow in the dark, these occasional flashes of light at the bottom of a gold mine. It's all very spooky, and I'm glad I'll be sending my grad students down there to do that scary work. The hope is that we'll be able to actually identify the particle that makes up the dark matter, but as far as the galaxy simulation is concerned, it has mass, and it pulls in other mass, it has gravity. That is actually enough. It's really remarkable what you can do with just knowing that base property. Excellent question. All right, right at the back I can see there's a hand up. Yay! Yes. Can we go to the microphone? Excellent. Just say your name. Oh, that's okay. Your parents are not going to have to speak instead and ask the question. No, that's a definite no. Astronomy is hard. There are no silly questions. Yes. Oh, in the front.
Hi there. My name's Socrates. First of all, comment. It seems that all you guys are really happy. So, is that something about astronomers? I mean, is this where we should be going for a career? It looks like you're playing rather than working, which is really nice to see. Then I had a question. Seems to me that, I saw a hydrogen atom up there, and I understand that's spinning, and we're on the Earth and it's spinning, and the sun's spinning, and our galaxy's spinning, and the local group's spinning. Is it true then that the whole universe is spinning? And if it is it slowing down or speeding up? Or?
Vanessa, you do high velocity stuff?
Well, when I was doing my PhD, I used to say I would extend the universe as far as the Magellanic Clouds because I was studying the Milky Way and those were kind of interacting with it. And then when I transitioned into the work I'm doing now, we're now going up to what we call redshift 1, which is about, I guess, 8 billion light years in the past. At that level, what we see, I mean, individual objects do spin because of the conservation of momentum, so they kind of settle. Similar to Saturn's rings, like that kind of physics holds at a lot of different scales. And Luke can probably add to that, but in kind of galaxy scales, I don't know if the local group is spinning, but they are certainly, the galaxies interact with each other, so they have an area around them which can determine, you know, how close am I to this, I can influence the gravity of that. Whether that translates into a spinning motion. Luke?
You can get a long way in theory by asking the question, what's fighting gravity? So if gravity is trying to crush everything because it's always attractive. So the Earth's spin, for example, isn't what's fighting gravity, it's solid, right? But in the solar system, our orbit, it's that rotation which fights gravity. If nothing is fighting gravity, you just have a black hole, because gravity is just one, okay? The universe as a whole, so rotation, so spinning around is one way to hold off gravity just completely crushing you. So there are a lot of things out there that are spinning. The universe as a whole, though, is expanding, and that's how it's sort of fighting gravity. It's expanding like this. So we could detect if the universe as a whole were rotating in that baby picture of the universe. It would actually be twisted in a certain way. So it's a very strong constraint on the fact that actually, no, it's not spinning. Which is funny because I'm going to go into sort of Scientology territory again here. Einstein's ideas about how gravity work involve space-time itself being twisted and contorted. So you imagine that space-time itself is warped, and that's how things work. He had a conference in his honor in 1949. And one of his friends, a very famous mathematician called Kurt Gödel, came up with attended with a birthday present for him. He had a solution to Einstein's equations for a rotating universe, and it proved that if the universe is rotating, you can have time travel. You can actually go backwards in time. You could play a game of poker with yourself. That unfortunately doesn't happen in our universe, but weird things happen if the whole universe was rotating. So far as we know, it's not. It avoids being crushed by expanding. But yeah, that's.
So is it then that everything in the universe is spinning except the universe itself?
Everything? A lot of things. It's not necessarily the case that things are spinning to hold back gravity. So that's not true of the Earth. But sort of conservation of angular momentum. Once things start spinning, once they start to contract, they'll spin faster. So even the slightest bit of spin, when you're a big diffuse cloud of something, when you collapse down, you'll spin even faster, more appreciably.
I'll just jump in on that one. You will have galaxies will spin one direction, and they'll actually, the reason they're spinning that direction is because they torqued up another forming galaxy that's spinning the other direction. So everything's spinning, but half of it spins one way, half of it spins the other, and that cancels out. And actually, we wanted to test if that were true. This was a big data project, a big data storage effort from Galaxy Zoo. One of the efforts that Liz mentioned at the end, and they wanted to have people look at this data and see how many times is a galaxy spinning one way, how many times is it spinning another. And they found that it was pretty much even, and I mean almost exactly even, except for this slight preference that they would be spinning right ways rather than left ways. I mean, like a fantastically small level. Like 1 in 10,000 galaxies might spin slightly more one way than the other. But they had so many millions of people working on this that they could actually identify that. I thought, wow, this is crazy. It means that the universe might actually prefer to spin one direction over the other. That's huge, and you get time travel. Except it turns out that people are biased, and their eye tricks them, and they think they're seeing it preferentially spin one way or another. So we actually learned something about human psychology by asking millions of people to look at these galaxies and test out this understanding of the spins of these objects. So an amazing example of what you can learn through making this data available, as Liz has done, for example. All right, have we got another question? Okay, we've got a few. Let's just go, yes, second, yeah.
Firstly, thank you for a fabulous event today. My name's Kim. I had a question about, I'm sorry, the last speaker's name.
Liz.
Liz, the global data network, the number of them that are being developed, does the, with gravitational waves detection, does that data from the LIGO project feed into any of those?
I don't actually know. So we have like a set of protocols that people have to follow if they want to get their data online and into the virtual observatory. You can't just put in any sort of data, you know, here's my picture of my dog. Like, it has to be some type of astronomy data, and you know, like, it has to be a spectra, right? And it has to have information with that about what it's of, things like that. If they've produced catalogues, so tables of results, then yes, that would fit in. Do you guys know if it's
I can add to that just because ASCAP was a little bit tied to the most recent detection of gravitational waves and a few of the kind of alarms that were sounded before that. So because at the moment it's such a new field and it's very protected, there's a lot of different groups around the world all trying to be the first to detect gravitational waves, so just one. But because of that, there was, I think it was like an embargoed thing where like they would sound an alarm, send it notifications to different people at different telescopes around the world and say, look, we think we have a detection, can you follow it up? And then they would follow it up, but it was all very secretive. They weren't allowed to tell the rest of the astronomy community. Of course, it kind of, in a weird way, gets out a little bit anyway. But yeah, so until I think feeding into the virtual observatory will take longer because at the moment it's such a hot field that everyone wants to like keep it under wraps until they're sure they actually have it, because they're actually really also pushing the boundaries of our instruments to try and detect these things in different ways. And so yeah, so I actually remember because at Sydney Uni, a few of the radio astronomers there were leading a paper that was looking at, so they followed it up with ASCAP and I think the compact array, and this paper had something like a couple thousand authors for a non-detection of radio waves coming from the source. So it's a bit complicated at the moment, but eventually, yes, we will have tables of detections going into it.
Awesome. Where's the microphone here? Let's go right back in the white, yes?
Hello, my name's Craig. A while back I was watching a Stephen Hawking program, and almost as a throwaway line, he sort of said the mass of the universe is balanced by sort of the empty space in between. And he had sort of like a pile of mound of stuff and a hole in the ground. He sort of made the equation that they were sort of similar. Given that the universe is expanding and empty space has an energy to it, are we increasing the net amount of entropy? Is the energy getting bigger, or is it a closed open system? What's your thoughts?
Do you want to take this?
Have a look.
The dirty secret of cosmology. Yeah. Energy is not conserved in the universe as a whole.
For physics, if you're doing physics at school or uni, it's always conserved.
So tell your teachers never write that on an exam. Okay? This is the dirty secret. So in the sort of the deepest language we have of physics, the conservation of energy is related to time symmetry. So your system you could just hit rewind and the same laws would apply going backwards and forwards. That gives you energy conservation. Because the universe as a whole is expanding, it doesn't look the same in either direction. And so actually, as it gets, if you had a closed universe, so if you had a universe with a finite amount of space in it, and it expands, it gets bigger. There's literally more space. My co-author likes to say that you could fit more oranges in the universe tomorrow than today. And if say dark energy is real, it's out there in space and it's constant as a function of, you know, you open up a bit more space and hey, there's that energy there, then the universe is simply gaining energy. Now, it's not doing that in a random way, and if someone tries to sell you a device that will power your car through the expansion of the universe, don't buy it. It's changing in a very predictable way. We haven't completely lost chaos, but the universe as a whole is a different kettle of fish entirely to the rest of the universe, the rest of physics as we know it, which does obey this principle of time symmetry, and so energy is conserved.
All right.
Everyone forget that?
Yeah.
Never said anything.
Okay. Just at the front, yes. Sorry. Thank you.
My name's Ruth. It might be a silly question, but I just wondered about the great attractor. Are we really being pulled toward the great attractor? And could that be that from the black holes that are all around that, the gravity from them, could that be what's dark matter?
Who was it? You do radio, so you see these objects.
I don't think a lot about the great attractors.
Oh, okay. Do you want it?
Well, it is just the only thing it is that we do not know exactly what it is because it is behind the Milky Way. So we see the galaxies moving, and we see that the galaxies are moving to a very particular, that attracted to a particular place behind the Milky Way. We should use radio telescopes to go deeper in those places of the galaxy just to try to see where it is. But that is what it was called the great attractor. It is just that. It can be a large galaxy cluster, like Coma or something like that. I don't know if you have some extra info about that.
It's huge. There's an enormous amount of material,
It is huge.
and I mean millions of times the size of the galaxy. Well, the galaxy is what, 100,000 times. And that's not, and black holes, while they will definitely be there in the center of all, indeed they're in the centers of all galaxies, 1 million, if not 1 billion times the mass of our sun. That's actually a very small fraction of the galaxy. So most of what we're feeling, this pull, is because there's dark matter, huge pools of dark matter, and it's pulling in all the galaxies from all around. So it's a great attractor. And yes, radio would, in fact, Lister and René Cordovet, they just did their zone of avoidance survey, and they actually peered through the Milky Way galaxy using radio telescopes, most predominantly which from Australia, and they saw indeed there were galaxies hiding behind us that were also falling into whatever this thing is. But yes, we still don't know exactly why it's as big as it is. All right, let's see, where are we going? Right at the back, yep.
Hi, I'm Zach. May I ask you, what's the purpose of understanding the universe?
What's the purpose of understanding the universe? I love it. Great, good question, Zach. This is a question I get, that's the first question I get actually on media. But yeah, who wants it? Yeah.
Because you want to understand yourself, who you are, where you're coming from. So we have been talking a bit about stars and about galaxies, about how stars are this kind of, I try to say the kitchen of the cosmos, no? Because they are really synthesizing elements into other elements. So at the beginning of the universe, in the Big Bang, only hydrogen and helium, these very light atoms, elements, were created. The rest of the other elements, oxygen, carbon, neon, iron, uranium, just name it, have been created inside the stars or because of the action of the stars with the surrounding. So you are made of star stuff. Your atoms were cooked in stars that were born and died billions of years ago. So we in astronomy and in science, we really try to understand our origins. The way that we are really connected into the cosmos, not following any of this kind of astrology or pseudoscience, but very, very deeply. And I think it is a very nice thought.
And I can also add to that because it is a question we do get a lot. And the reason for doing it, one of the reasons is because when you're exploring the universe and asking questions about things that seemingly have no relevance to your daily life, you actually discover things along the way. So a lot of people often talk about, so if you've used Wi-Fi before, you can thank evaporating black holes for that, because actually it was astronomers trying to find a better way to study evaporating black holes that led to Fourier transforms on a chip that led to Wi-Fi. So until you study what's around you and understand how it works and what it's made of, you don't know what we're capable of doing. So that's one of the really important reasons, because we need to know what can we do in the future, and that comes from understanding things at the quantum scale, quarks, all the way up to galaxies.
Are you happy, Zach? Are you still skeptical? You are? Because it's cool, Zach. You do it because it's cool. All right, excellent question. Let's bring it back to back to the front, and then we'll go to the white.
Thank you. I'm Brian. Is there a critical mass at which gravity kicks in?
Critical mass. Gravity is always present. Any mass will experience gravity and will cause gravity on something else. Do you mean for maybe forming black holes, or?
Just objects in the universe. Is it like the biggest is the attractor?
So the bigger an object and the closer it is, you're going to fall towards that.
Yeah.
You can be precariously balanced between two big objects, but if you just happen to be closer to one, you'll fall to that. But everything in the universe is pulling on you right now. Every star in our galaxy, every galaxy in the radio images you saw, all of those are connected to us by gravity, and we in turn are pulling back on them, but a tiny, tiny amount. I mean, the most important thing is, of course, the Earth, which is the closest to us.
Second quick question, spectral analysis. We look at light coming from various bodies in space and do a spectral analysis of that light. If it's coming from, say, 2, 3, 4 billion light years away, surely it's heavily filtered by the time it gets to us, and therefore nothing like the original composite in terms of wavelength. Therefore, what we're reading is erroneous.
All right,
Well,
let's talk about
so,
that.
I mean, I can comment on the radio side, but maybe Angel wants to say something about the optical
that
side.
is actually very important, and it is one of the very first things that we have to do at the very beginning when we have our spectrum ready to be analyzed, is to be sure that we are measuring the same light that was emitted by the object that we are trying to understand. And there are plenty of things in the way. And it's starting with our own atmosphere that we have to deal with, with the Earth's atmosphere, till clouds of gas, other galaxies, diffuse stuff there. So we have to correct that. There are some techniques just to try to do it, and we try to, and we do that. So we correct for this kind of absorptions of the light that is coming from the universe, and then we analyze the data from there.
So on the radio side of things, so with the hydrogen atom, you have this expected frequency, so 1420 megahertz, 21 centimeters, about this big. And so if you say, I want to see if there's hydrogen in this galaxy, and you know how far it is away, when that light redshifts, it appears at a set frequency. So at least in the hydrogen case, it's very simple, because you see a line there at the place where the galaxy is, or you don't. But interestingly, on that line of things, so the MWA, those spider telescopes I showed, so they started operations, they were observing the sky, and I think she was an undergraduate student at the time. She was working on this, trying to image the data and see what she saw in it. And she was seeing these weird structures that didn't look right. They were kind of like tubes, they had different colors, like if you did the kind of intensity, they were moving across the sky. And it was because she looked at the data and really tried to understand what it was showing that she discovered that we were actually seeing plasma tubes in the atmosphere that had been predicted many years ago but never actually detected. And the MWA, because it's spread out over so many kilometers, they could use parallax, which is just crazy. So they could use one side and this side and actually triangulate what height in the atmosphere these tubes were. So I guess the answer to the question is, when we look at our data, and obviously with bigger data we're not going to have a chance to look as deeply, but when we look at our data, we make sure we understand what we're seeing, to understand if it's showing us what we expect or not.
The short answer is that space is really, really empty. Just really, really empty. So the density of air in this room is a billion times higher than the average density of the universe, right? We've never made a vacuum that good on Earth, but that's the average density of the universe. There's just nothing out there, right? And we know what it would look like if a light source at the back came through and scattered off things on the way. It would look like a fog. It wouldn't look crisp. This lovely crisp image of the sky, you wouldn't see that, it would just be blurred. So that actually puts constraints on how much stuff could be in the way and what sort of stuff could be in the way.
All right, there's a question back in the white. Yeah.
Yeah, my name is Nicole. Just to follow up on Zach's question, because with all this study, I mean, by now we probably know a sufficient or significant amount of data information about the universe. But continuing on, is there anybody or different group is actually using those data to study what can we use or what can we make out of that to benefit our Earth, or what is prospect in the future? You can continue studying what's out there and keep collecting all this data, but we probably have not enough human capacity to understand the whole lot of data we are going to collect. But even with those data we are collected, what is the significance of that? But we understand some of the things that is already working, but what is actually the function of what can you use or make out of that?
Okay, so what value can we get from taking more data? What are we hoping to see and hopefully inform on Earth? And how can we do that when we don't have enough people to analyze the data we currently have? Liz?
Well, big question. Well, humanity will always progress, right? There's always benefit to building bigger telescopes, better telescopes, and taking more data. I suppose the way that we're going to handle it is this machine learning, right? So it doesn't really matter anymore that we don't have enough humans to look at the data. We train programs to look at the data for us, and then that kind of brings new questions and answers for us. As to how that benefits humanity, what was the rest of the question?
Well, I guess what are we hoping to discover?
Yeah, I'll hand over to the astronomers for that bit.
Well, so I mean, one thing I always love is like, and not even just one person, but a couple of people were very famous for saying at the start of the 20th century that we'd learned everything there was to know about the universe. Okay, so 1900, everything's done. Think about how much has changed since then. It's very hard. Like, I mean, most of the things that we've discovered along the way weren't predicted in any way. It was people kind of like exploring new technologies, developing things, following paths that sometimes led to dead ends. So while there are, and other people can say what kind of specific questions we want to answer with the new generation of telescopes, a lot of it is also just probing the unknown. I mean, I honestly hope that our space industry grows as a planet, and that by exploring not just from Earth, but also through the solar system and beyond, that we'll learn things that we can't even imagine today. I mean, if you went back to 1900 and tried to convey what life is like today to people then, you'd probably be committed to a mental hospital or something. Like, it's just so different. So I think that, and I think the change is also getting exponentially faster. So, you know, with so many people on the planet all doing different things at once and all kind of communicating really clearly with virtual, I mean, in our case, virtual observatories connect astronomers around the world, the internet. It's really hard to say where we're going, but we still have a lot of big questions about astronomy to answer. For example, would you guys like to?
I would like to add regarding getting a lot of galaxies authentic. How many did I say for Hector in particular at the 80, 10, 100,000 galaxies? The thing is that we really want to explore how galaxies are evolving and how they are acquiring some properties, let's say mass, let's say how giant stars, older stars, the elements, how the chemical composition of the galaxies are enriched as the time is going, star formation, and many other properties, and how they're moving and whatever. So for doing this in a really clear, nice way, we really need that huge amount of data, because we have to break everything into small categories, and then use statistical tools in some way that we can extract from there the general rule, the general properties, the general things that are ruling galaxy formation and evolution. And for that, really, we need a lot of data.
I might just also add, on a very personal level, we have this dark matter detector, right, we're trying to build here in Australia, or building in Australia. The reason we're so excited about understanding dark matter is because we're done from the idea of particle physics right now. The Higgs boson, the God particle, was the last piece of the jigsaw, and we completed the jigsaw, and we found we had entirely other bits out there, right? Other pieces like dark matter, dark energy. We don't know how the universe began. There's lots of questions, and gravity isn't even included in that model. So there were lots more questions, but there's no obvious direction to take it. And dark matter is one of those key things we know that is weird with the universe, and we can try to hope to find what it is, and that will guide particle physics on a new direction, a new understanding of nature. And that is the reason that the Large Hadron Collider was built, the atom smasher in CERN, and actually you can explore that without going to Geneva from the 11th of August, because they're bringing the Large Hadron Collider to you here in the Powerhouse Museum. And then you'll actually be able to explore the whole setup. It's called Collider. It's absolutely incredible. And you'll be able to see and get a sense of the scale and the discoveries they've made. And along the way, on their journey to discovering the Higgs boson, they've developed technologies that have led to cancer treatments. Right? Cyclotron that prepares radioactive material, or PET scans, or even directly targets radiation to kill cancer cells. That's come from particle physics. So while some of the things that we want to discover, so like the Higgs boson, which is arguably quite tricky and abstract to understand, we invented and created solutions to those challenges that then find huge importance in the world around us. And I can expect just as great change is coming in the next few decades, as Vanessa alluded to. Maybe just one last question then? Yep, okay. You get the last question.
Thank you, and thanks to all the speakers here. My name's Rob. I have a son who's interested in particle physics, and what really strikes me is that if the people on the panel were looking back 25 years ago, what they seem to be practicing now may have been theory 25 years ago. Where do they see in the next 25 years with the exponential growth of AI, etc.? Where, if this speech and talks were given in 25 years' time, what theories today would you hope might be in practice at that time?
That is a really good question.
I had a crystal ball. So 25 years ago, the sort of simulations that I talked about were actually being done on small computers, and those simulations now you could do on a computer in the, they took a month and they can now take you like a lunchtime. Where would you like to be in so there's other windows on the universe. We've talked about optical and radio. There are other types of particles out there, so neutrinos, for example. If we could see those, we'd see a lot of stuff. The gravitational wave window has just opened up. It's like learning how to hear. It's that sort of change in how we see the universe. We can see it, now we can sort of hear it. So we can sort of hear things happening that are so small that we'd never be able to see them. They don't send out enough light for us to see them. But that's a massive open window in the universe and all sorts of scales. So the sort of things that are theory now, I mean, these simulations, there's a lot of detail in there that we really don't know whether that's really how galaxies work. For example, one of the way that gas gets its final plunge into a galaxy is often along very thin streams, cold streams coming in. That's in a lot of simulations. We still don't quite know whether that's really how it happens. That's what the simulations say, but could we get out there, could these new observations actually see that sort of thing happening? That would be amazing to see, because that would sort of vindicate some of the ideas, or even better, prove us all wrong and we have to guess again.
All right, so to summarize, you were hoping gravitational waves and cold streams?
Yeah, some more funding for myself, that sort of thing.
Vanessa?
I mean, so very quickly touching on the cold streams, so one of the projects I'm working on, we were looking at the halo of the Milky Way, and one of the big questions with the Milky Way is, these are how many stars are being born in our Milky Way every year. This is how much hydrogen we're getting in every year. It doesn't match. So I'd really like to see over the next 10 years, with the more sensitive telescopes and surveys that can do more detail than ever before and linking better to simulations, can we explain our own galaxy before we look to the rest of the universe? Can we explain how we got to where we are today? And I think in terms of the kind of game-changing thing that's going to happen, I mean, it's always been technology that's changed astronomy. So I think in the next 25 years, things like virtual reality, machine learning, if you want to go into a career in astronomy in 25 years, then that connection between data science and the science is going to be even stronger than ever. You can't just do physics alone. You need to be able to deal with this amount of data. Even, it doesn't matter if you're theoretical, it doesn't matter if you're observational, there's going to be a lot of data that you need clever ways to look at. So I think having a strong connection to the computing side of things is important.
Liz, I'm seeing you now for that.
Yeah, I think astronomy is going to kind of move into the cloud. It will be more you bring your code to the data rather than you dragging the data from these different virtual observatories. And solving the big storage problems, they're still not really sure how they're going to deal with the amount of data from the SKA. You know, we just predict that by the time it turns on, we'll have got that in the bag. So these kind of problems are kind of, help. Please, they're not so far away as you might imagine. They're kind of on our doorstep, and we're going to solve them quickly. We have to.
No, I just would like to say that I'm very sad. I'm very sad because I'm a romantic astronomer, so I really like to go to the telescope and feel that I'm under the stars and with my work and getting feeling the connection with the universe. But it is, in 25 years, it's not going to happen. I mean, we are going to have all these amazing data sets, and we have to dig in and try to get, using all these tools that we have been talking about, just to try to extract the data from there, but not actually going to a telescope. It is a bit sad about that. But on the other part, you will be able to understand much better how the universe works, which is something that's really, really cool, and that is at the end what we are trying to do today right now. Yeah, so I'm connecting that with the detection of the gravitational waves that are definitely opening a new window to the universe, plus, you know, all the ways of how galaxies really condensed and the filamentary structure of the universe, and seeing that in the diffuse, very low neutral gas, just to see that it is actually there, what we see. So, yeah, something like that.
So in terms of 25 years from now, we'll know what dark matter is, or else I will have well and truly lost the plot, because I'll be 58 and still wondering. We won't know what dark energy is. I'm calling it right now, Luke. It's just too weird. And I hope that we'll actually be able to know if parallel universes, multiverses, are truly there or not. We will have a handle on the grand unified theory of everything that eluded Einstein. And we will potentially be able to know if parallel universes. So we will actually have learned everything there is to know about our universe, almost, and hopefully maybe exploring other universes. That's where I hope we can be in 25 years, and you can be at that conference. All right, well, thank you so much for your excellent questions and your attention all day. Please thank the other speakers on the panel. And my thanks to the Powerhouse Museum, ViViD Sydney, ViViD Ideas, the AAO, ICRAR, University of Sydney, and Swinburne, for me, for making this all happen.
Thank you, Alan, for hosting us.